I want to take a moment to pause amidst all this theory, and there is a lot of theory, and in fact there's even more to come, but I want to pause for a moment to talk about applications. Presumably that's why most of you are here. I suspect that there was probably a conversation in an office in the engineering department that went like, yeah, you need this because it applies to the world. And it does, and the heavy machinery is still yet to come. But for the moment, a word or two about applications. We've generalized a number of results from, say, Calc 1, functions of one variable, to Calc 3, functions of several variables, and the applications generalize as well. So again, we're just working very small here, but it pays to pause and mention the very basic connection in Calc 1, namely that if you have on the one hand an amount, taking a derivative, say with respect to time, gets you a rate. Going backwards from rate to an amount is the business of integral, say with respect to time. Here I'm using dt because usually the simplest example here is, for example, amount of distance, and you get rate of change of distance or velocity. So if this is, say, in meters, then this is, say, in meters per second. But as I indicated several lectures ago, this is a special instance of the more general phenomenon relating not amount, but really accumulation or total, to not just rate, but to ratio. So a bit more generally here, I can sort of think of this as accumulation and this as ratio. And again, on the one hand, derivative doesn't have to be with respect to t, but I'll just say ddt for derivative. And to go from a ratio back to accumulation is done by integrating. I think, again, a good example here is, say, mass. In kilograms. A ratio is not mass, but say, for example, density. It's density because the ratio is in kilograms per, and for the moment I'll say meters squared. The reason is we don't yet have the vocabulary to talk about meters cubed. Actually, the reason it's squared is because when we had a function of one variable back in Calc 1, I could only talk about mass per 1 unit, mass per meter. Now we have two variables, I can talk about density as mass per meter squared. Eventually, yes, we want 3 variables to talk about the real world, and I guess that leads to some of where the heavy theory will go. But again, for the moment, consider, for example, a lamina, which is a word I was convinced was completely made up. It's a thin sheet that has no discernible thickness, so you can pretend as though it's got 2 dimensions. So suppose a sheet, or suppose a lamina, to use the book's terminology, just means a 2D sheet, has density function rho of xy is equal to y squared e to the 2x kilograms per meters squared. So whatever this looks like, at least now we're able to talk about the density of a sheet as a function of x and y. So density at the point AB is given by rho of AB. Back in Calc 1, we could only have a function of one variable, so we could just do density, say, of a one-dimensional wire. Here now we're growing to 2. All right, suppose it's got this density. Find, for example, the mass on, let's say, a sheet, or for a sheet with dimensions x is between 0 and 2, and y is between 0 and 4. All right, well, this is really just a double integral in disguise. As I said, just a couple words about application. So to get this mass on this region, I'm going to be integrating over, say, the region D, or really I suppose it's R, rectangle, defined by these dimensions, the density function, rho of x, y, dA. Once again, just like differentiating an amount gets a rate, integrating a rate gets the amount back, or differentiating accumulation gets a ratio, integrating that ratio gets back accumulation. Differentiating mass with respect to meters squared would get rates of change of densities, but the integrating density will get us accumulation of mass. So here, then, I get, 0, 2, 0, 4, y squared, e to the 2x dy dx. All right, not thrilling, pretty standard fare. This is integral 0, well, I guess I can pull the y through, can't I? 0 to 2 y squared dy, integral 0 to 4 e to the 2x dx. This gets me y cubed over 3 from y is 0 to y is 4 times a little bit of u sub, so e to the 2x over 2 from x is 0 to x is 4, and this will be 32 over 3 times e to the 4th minus 1. Units here, I suppose, are important. Kilograms, because I'm integrating a ratio density to get a mass. I do want to lean into this relationship that I keep emphasizing. Specifically, the relationship between accumulation and, say, rates or ratios. And the, specifically, relationship established between the derivative, which goes from, say, accumulation to rate, and the integral, which goes from rate back to accumulation. Presumably, you've seen this a number of times. It's usually rolled out in a rather intimidating form. It usually looks something like this. Given a whole bunch of nice conditions, so put a bunch of stuff like here, given a lot of nice stuff about little f and capital F, etc., you had something that looked like the following. Capital F of x equals the integral, say, from, well, simplified a bit, 0 up to x of little f of t dt. Yeah, this was a simplified version of the fundamental theorem of calculus. But I want to examine what this says, because it's very much a preview of the heavy results to come. Consider this f of t as a rate function. So f of x is integrating this rate function. Usually, this is shown as follows. So if you like, you can think of it as a rate function. Say, I'm a little loath to do this, but we'll take velocity. Keep also density in the back of your mind. And say that it has a graph that looks like this. So this is the graph of f of t. Now, I know that t's and the x's can get a bit confusing. The point is that you've got a function of t, little f of t. Here's the t variable on the x-axis. Here's f. And it's a rate function or a density function. You know, I guess from Calc 1, that this integral, say from 0 to 1, would be the area under f between 0 and 1. The area, the integral between 0 and 8, the area under f between 0 and 8. The integral from 0 to x, the area under little f between 0 and x. Area under little f between t is 0 and t is x. So if you like, you can think of this as a velocity function, and I'm integrating the velocity function between time 0 and time, I know it seems a bit weird, x. The reason I chose x is I don't want a fixed time. I want to let it vary. Here then is the upshot, the f, or one of the f fundamental parts of the fundamental theorem of calculus. Yeah, it's true that you are getting area when you integrate under f of t. What's more, I can let this x or t value vary, and so the area will vary. I therefore don't just get the area underneath f between 0 and 1, or the area underneath f between 0 and 10. I get the area under f between 0 and any time x I like. In fact, this could be called the area function. It's a function of x. How much area do I get when x is 1? How much area at x is 11? Because I can interpret this f as a rate, if this is velocity, this area means distance. On the other hand, let's say I'm integrating density. Namely, let's say we'll stick with one variable, density with respect to short t, rho of t. This then will be a mass function. The farther out I move t, the longer whatever this thing is that I take the density of, the more mass I'll accumulate. In this case then, if I integrate rho of t, I'll get not an area function or a distance function, I'll get a mass function. This is the important, at least, connection that most likely your Calc 1 teacher tried, or maybe didn't, to bring home. The connection between integrating a density or a velocity or any kind of a ratio to get an accumulation. If you've done any stat, you integrate probability density functions to get, well, what's the probability that something happens? Bring us back up to Calc 2 because we now have density functions of not just one variable, but two. We'll scale this up to a relationship between accumulation of 2D and accumulation and density of 2D. Likewise, we need to get to the real world, so we'll talk about accumulation in 3D and density in 3D. So, still to come. The relationship between accumulation and ratio in 2 and 3 dimensions. As you might expect, you get it in 1 dimension with a function of 1 variable. Here I'm going to need a function of, well, 2 and 3 variables. Require function of 2 and 3 variables. It's still a ways off, but for the moment, if for no other reason, I would like you to begin to think about integrating density to get accumulation. Area was only ever one very easy way of visualizing it. The physical significance is far more profound. Before I return to theory, and there is a lot of theory to return to, let me get just one more application, since really it's right in front of us. Not mass, but something closely related. Center of mass, a physical phenomenon I suspect many of you are familiar with. And for the moment, I'll do center of mass of a lamina. Remember, that's just a fancy word for a two-dimensional sheet that, for the purposes of calculation, doesn't have thickness, on region D, say in R2. Physically, this iPhone has mass, or at least it must, since I keep dropping it. However, it also has center of mass, presumably where I would balance it so that it wouldn't fall. The center of mass has coordinates. Now, this iPhone definitely does not have uniform density. It's going to be, say, denser at the edges, maybe where there's more metal, than in the middle, or vice versa. I'm not exactly up to speed on iPhone density, but it doesn't just have mass that would be integrating the density over this region. I can find its center of mass. And the center of mass of an iPhone or a lamina or anything else that we can treat as two-dimensional on a region, D in R2, which has coordinates denoted by X bar and Y bar. So center of mass of lamina on region D, X bar, Y bar, given by X bar is equal to 1 divided by the mass, so 1 over the mass, times the integral not of the density function, but of X times the density function dA. And here I'm taking the double integral over the region D. Likewise, the y coordinate of the center of mass is 1 over m, double integral over the region of dy, rho of xy dA. Boy, I'm leaving out some fantastic theory here. This integral part without the 1 over m is the moment, the x and the y moment. And there's some fantastic averaging happening in here that makes this a great segue to probability theory and statistics. But just back to the calculation, I'll do an example. So, for example, and I suppose here I should say, of course, m is mass. So then, for example, find the center of mass. Find the center of mass. To squeeze in as much as I can. CTR of mass of a triangular lamina with vertices 0, 0, 1, 0, and 0, 2, and we'll say density function given by rho of xy is 1 plus 3x plus y. So let's at least get some sketch of what's going on here. Here I've got, let's see, vertices 0, 0, which is there, 1, 0, which is there, and 0, 2, which is there. So I'm integrating a density function over this region. It should be clear that we are definitely not looking for the area of this region, the usual Calc 3 mistake when we first start playing with double integrals. Here is an interpretation of what a double integral is. Rho of xy tells me what the density is as x and y varies. So for example, the density of this thing at 0, 0 is 1 plus 0 plus 0, namely 0. At the edge here, 1, 0, the density will be 1 plus 3 times 1, 4, plus 0, or 4. So it gets more dense as we move out. Finally, in order to get this moving, I need to describe this region. It's obviously, I think, easy both up, down, and left, right, but I need that line that connects those two vertices. Quite clearly, this is the vertical line, x is equal to 0. This is the horizontal line, y is equal to 0, and a bit of quick y equals mx plus b gets me y is equal to 2 minus 2x. Okay, so first I need the mass, then I can find my centers of mass. So the mass, again, is the double integral over this region D of rho of xy dA. At this point, the integration is straightforward. It's the interpretation that matters, so I'll skip some of the steps. This will get me, let's say, I guess we'll go up, down. So inner bounds will be y, outer bounds will be x. So this will be double integral of, where am I? 1 plus 3x plus y dy dx. Inner will be 0 to 2 minus 2x. Outer will be 0 to 1. I need the space, so I'll go directly to, this becomes the integral 0 to 1 of 4, 1 minus x squared after integrating and plugging in, dx, and this eventually gets me 8/3. All right, yeah, I'm skipping steps. If you have questions, totally post on discussions, and I'll totally answer. So, what then of the x component of the center of mass? It's going to be 1 over m, double integral over the region D, not of the density function, but of x, times the density function, dA. All right, so this will be 1 over 8 over 3 times the double integral. Again, I'll go up, down, left, right. So 0 to 2 minus 2x, 0 to 1. And now it's going to be x times 1 plus 3x plus y dy dx. This is now a straightforward just double integral over the region described there. So this will be 3/8 integral 0 to 1, integral 0 to 2 minus 2x, and then of now an x plus a 3x squared plus an xy. I want all of this on one board, so I'll cut to the chase. Dy dx, this will get me 3/8. No, that's not a typo. It just turns out to be that this entire double integral is 1. However, y bar, which is now 1 over m, I guess it's time to get back on the floor, double integral over the region D now of y, rho of xy dA. Again, this will be 1 over 8 over 3, double integral, inner, 2 minus 2x, outer, 0 to 1. Now it's a y times all of these guys. So it'll be a y plus 3xy. And then plus a y squared dy dx. And again, I leave it to you to fill in the exciting details. In the end, this will be 11/6. All right, what does this mean? I need a little bit of space for an interpretation of what I've got. Namely, if, again, here's the region, there's 1, there's 2, D. These coordinates are the center of mass of this region, and not surprisingly, it lies inside of the region. Namely, it'll have x coordinate 3/8, which is between 0 and 1, y coordinates 11/6. Notice, by the way, a bit more accurately, it's up there, awfully close to 2, namely 12/6. So 11/6. And the reason that's true is I'm not looking for the geometrical center of this thing. This thing has variable density. It gets denser the farther out you go. So it's not surprising that I wind up with a density that will, or a point for density that will be, toward the edge. Once more, it's not the center of the object. It's the center of mass of the object. The geometrical center would correspond to the center of mass if we had uniform density. Quite clearly, here we don't. It's denser at the edges.